section. We're going to talk about similarity transformations. Yesterday, we did congruence transformations. They're very similar, but one slight difference. A similarity transformation is a composition of isometry, meaning rigid motion, so translation, reflection, or rotation, just like what we did yesterday, and a dilation. In order for it to be a similarity transformation, you have to do a dilation. If you don't do a dilation, then it's a congruence transformation. Okay? By definition, two figures are similar if and only if there is a similarity transformation that maps one figure onto the other. In other words, in some sort of rigid motion, let's just say a translation, so you slide the figure. Then you do a dilation. Right, so you make it bigger or smaller. That makes it a similarity transformation. Okay? So a good indicator on whether or not you did a congruence transformation or a similarity transformation, if you're doing a dilation at all, at any point, it's a similarity transformation. If there's no dilation, then you know it's a congruence transformation and those two figures are congruent. Okay? So we look at this first example, we have triangle DEF. Let's go ahead and plot those points. 0, 1, 4, and 4, 2. E, E. There's our pre-image. We want to take this triangle and undergo these transformations. What's the first transformation we're doing? First transformation we are doing. What's a capital R stand for? Reflection. Capital R is reflection. What are we reflecting over? Y-axis. What's the second transformation we're then doing? Dilation. Good, capital D stands for dilation. What's the scale factor? 1.5. Very good. So we do this first transformation, we're reflecting over the y-axis. I'm going to highlight it. You can darken it with your pencil or use your own highlighter. And when we do a reflection, all you're doing is just counting how far each point is away from that line. You count the same direction, same amount the other direction. So how far is E away from that line? 1. You go 1 in the other direction. How far is F away from that line? 4. So you go 1, 2, 3, 4 in the other direction. How far is D away from that line? You go 1, 2 in the other direction. Okay? That's not our final image. That's just what that triangle would be when we reflect it. Okay? When we do our next transformation, which is a dilation, what do we do? What operation are we always doing? Multiplying. Right? Are we going to multiply the original image or our new one we just plotted here? Yeah, the new one. Okay? So write down the new points that you just got. We have E is 1, 4. F is -4, 2. And then D is -2, 0. Is it -1, 4? Thank you. And then you're just multiplying the whole point. Whenever you see a dilation, you're always multiplying by whatever your scale factor is. Okay? So when we multiply this point, what's -1 times 1.5? What do we get? -1.5. What's 4 times 1.5? 6. Very good. What's, and we said 4 times 1.5 is 6. So negative 4 times 1.5 is going to be negative 6. That's 2 times 1.5. Double 1.5. 3. And then here, 2 times 1.5 is positive 3, so negative 2 times 1.5 is going to be negative 3. And then 0 times anything is what? 0. So now, you just did our last transformation, we're going to plot these points, and that's going to be our final answer, our final image. We have negative 1.5, is right in the middle, 1, 2, 3, 4, 5, 6. That is E prime. We have negative 6, 3. That is F prime. And then we have negative 3, 0. E prime. Questions over that? Again, it's just like what we did yesterday, except we have a dilation involved. Alright, take a look at the next one. All we're doing is what we did yesterday. We're going to match.
And it's the reverse of it. So let's get moving here. So now we want to see, again, it's the reverse of what we did. Determine the similarity transformation that maps RST to triangle PYZ. One thing I'll just talk about from yesterday real quick. One of the issues we saw was, first off, a lot of you guys weren't writing your points down, and that's not good. For dilation and rotation, here's it. Again, open your ears for this. For dilation and rotation, you better write down those pre-image points, because you're going to have to change those to either rotate it or to dilate. So you have to write those points down. For translation and reflection, you just count. That's easy. But definitely write down the points. So let's see what's going on here. We want to map RST to PYZ. So it tells us where to start. Which triangle we started with? The little triangle or the big triangle? The little guy. Or girl, I don't know what it is. Well, the little one right there. So how do I get that one over to where the big one is? What do I need to do? A couple things. One thing, what do I do? Well, one thing I want you to look at is this. Let's look at the points. Because remember, the points match up. The order matters in these triangles. So RST. So R matches up with what other point in the bigger triangle? R matches up with P. All right. So there's R, there's P. They go together. S goes with Y. Because I told you so. S goes with Y. Well, look where they're at. S is up top up here, and Y is on the bottom, and then T goes with Z. T's over there, over there. Someone said, is this a reflection? And I say it could be a reflection. It could be a reflection of where Y equals negative X. So that line's, well, okay. That line lies right there. And it is. It looks like it's flipped across. But because of the points where they match up, since S is up here, if it was a true reflection across this X equals negative, or Y equals negative X, S would be right here. And then we'd have to dilate to get it bigger. But it's not. S is down here. So which property tells me to turn stuff? Which one allows me to turn? Yes. Rotation. So rotation, how much do we rotate? 180. Again, how do I know that? You just count the quadrants. We want to go counterclockwise. If I move 90 degrees, that's only one jump. It would be right here. It's not there. Go another one, that's where it gets me to that. That's 180. So we are going to do a rotation of 180. Because it's a rotation, you need to write down the points. Do you have to? No. If you want to be right, I would definitely write them down to keep yourself organized in your thought. So I'm going to write down these original points of the pre-image. SRT. Then we're going to do our changes to get where it goes. SRT. This is our pre-image again, remember? So S looks like it's sitting at a 1, 3. 1, 3. R is sitting at a 1, 1. And T is at a 3, 1. All right. You guys said great stuff. You want to rotate it. That's the only way to orient it. Flip it the other way around. So, what is the rule for rotating 180 degrees? What do I do? Yes. Perfect. No flip. Change the signs. All right, so it's going to stay the same. This will create out an S prime, an R prime, and a T prime. And the other one will be mapped on itself. If we do it correctly. All right. So, no flip. 1, positive 1, positive 3 now becomes negative 1, negative 3. Positive 1, positive 1. Negative 1, negative 1. And then positive 3, positive 1. Positive 3, positive 1, excuse me. Negative 3, negative 1. Awesome. Fantastic. Well, let's graph this new image and see what's going on. It might be graphed on itself. I don't know. So let's do S prime. Negative 1, negative 3. S. R, negative 1, negative 1. R prime. And T is at 3, negative 1. Or negative 3, negative 1, excuse me. And that's, you said T. Draw my little triangle. Awesome. It's in the same quadrant that I want. Is it the same shape as the large triangle, the PYZ? Is it the same size? It's not. It's the same kind of triangle, just a little bit smaller. So how do I get from the green triangle to my final triangle? What do I need to do? Dilate it. How much? Great question. How much? A couple of other ways to look at it. You could say, all right, well, is there any of those segments that are on a straight line that I can easily just count how long it is? Yeah, there's two of them. I can see what TR is or RS. And then compare it to the other one that corresponds to it. Well, let's look at TR. How long is that segment? 2. How long is ZP? 4. How much bigger is 4 than 2? It's twice as big, right? That's great. Sometimes it's really easy to see that. What if what if the triangle is not on straight lines? There's no horizontal vertical lines. How do you figure it out? Well, again, a dilation is a dilation. Write down the points. Okay? Let's write down the points of our final answer. And let's see how much bigger they are. So my final points, let's do what Z is. Let's do, hold on. Thank you. Got it. S goes with Y. So let's write down what Y is. Let's write what P is, and let's write what Z is. And then we'll see how much larger it is. And this is, if it isn't on a straight line, you can easily count and see how much larger it is. And sometimes it's weird because there are decimals and other things like that. So what are the points of Y? Looks like Y is at negative 2, negative 6. Negative 2, negative 6. P is at negative 2, negative 2. And Z is at negative 6, negative 2. Look at the green one compared to the red one. Again, we already said it, but how much larger is the red one than the green one? How much do the points increase by? All right, negative 1 becomes negative 2, negative 3 becomes 6. Oh, they're just doubling it, right? So multiply it by 2. So I have a scale factor of 2. And now we know we did. If I do so, it maps onto itself. So that green one would be in the same place as PZY. So now I can write my statement. I'll put it right above here. So I know I did 2 moves. What was the first move I did? A rotation. What letter represents rotation? Lowercase r. Lowercase r. So I put that lowercase r. How much should we rotate by? 180. I went diagonal with it. That's 180-degree rotation. 180 degrees. Okay, I was like that. I did a rotation of 180. Then, and what's my next thing I did? I rotated it. Then what did I do going from green to red? Dilation, as represented by a capital D. What do we dilate by? 2. So I'll put a scale factor of 2. That's it. That's what I did. And another thing is this. What did I dilate? Where did I start? Some of you guys left this off. We don't know where you started. They told us where we started. What triangle did we start with? SRT. This triangle over here. So I'll just say, all right, we took triangle RST is what they called it. I don't care how you label it. We took triangle SRT, we rotated 180, then we dilated it, and that's how we got our final answer. So that's how you tell if it's a pre-image or an image. Make sure you include that. Label your points, label your similarity transformation. All right, well, we've been doing this every single unit. Let's see what's the same or different. Last time we talked about when we did congruence transformations, everything was the same. Now we're doing similarity statement. Does that still remain true? Everything's going to be the same? I don't know. We'll find out. All right. Number one, angle Y and angle S. Are these angles going to be congruent from the first to the last? Will they be the same? Yes. Yes. Or no. That is the answer. Again, when I'm thinking about, this is the one where the size changed. If I have the world's smallest equilateral triangle and the world's largest equilateral triangle, do the angles change? So as long as the shape remains the same kind of shape, just gets bigger or smaller, the angles do not change. So this one, still the same. That works out for me. Starting with the big one and the final one, it's still the same. What about segments now? PZ and RT. Are these the same throughout? No. Why? Because it's getting bigger, right? It's getting bigger or smaller depending on what it is. So PZ and RT are not the same all the way throughout. So they are different. They are different. What about the old perimeter? Around the outside, around the outside. Does the perimeter stay the same, or does it change? It changes. If it's getting bigger or smaller, does that mean you need more or something? Yeah. It's going to be different. That changes. What about area? Yeah, that's going to be different. Again, it's the same kind of principle. If you have a bigger shape, it's going to take more area. If I have a small room compared to a large room, it's going to take more carpet to put on the floor. So yeah, that's going to be different. What about slopes? The slopes change? No, remember, in dilation, slope stays the same. So good. Thank goodness we got back to that. The slopes stay the same. I can make it big or small. The rise over run will still stay the same. So again, what we take away from this, in similarity transformations, the angles stay the same, the slopes stay the same, but everything else changes. Question with that? Okay. Well, the good news is, someone's going